Provability logic is a branch of modal logic that studies the concept of formal provability. In these systems, the modal operator, often written as a box, is interpreted as "it is provable that." Thus, a formula such as box A can be read as A is provable in a given formal system, typically a system of arithmetic such as piano arithmetic. Provability logic was developed in the 20th century as a way of formally analyzing the notion of proof within mathematics. It provides a modal framework in which statements about provability itself can be expressed and studied. One of the most famous systems of provability logic is GL, which is an abbreviation of Gödel-Loeb or the Gödel-Loeb logic, which captures many important properties of formal provability. In this way, provability logic forms a bridge between modal logic, proof theory, and the foundations of logic and mathematics. The development of provability logic is closely connected with foundational questions about logic and mathematics, especially those arising from Gödel's incompleteness theorems. Gödel showed that sufficiently strong formal systems cannot prove all true statements about arithmetic and cannot prove their own consistency, assuming they are consistent. These results raise deep questions about the nature of proof, provability, and self-reference. Provability logic provides tools for studying these questions in a systematic way. It allows us to express statements such as, if A is provable, then B is provable. It is provable that A is provable. Or, if falsum is not provable, then it is not provable that falsum is not provable. The last sentence is a possible reconstruction of Gödel's second incompleteness theorem. Another motivation is methodological. Instead of reasoning directly about complicated arithmetical proofs, provability logic abstracts their essential properties into a modal framework. This abstraction makes it possible to analyze general principles governing provability. The syntax of provability logic is typically the same as that of propositional modal logic. Formulas are built from propositional variables using standard logical connectives such as negation and conjunction. In addition, the language includes a modal operator, the box. The intended interpretation is that box A means A is provable. The dual modal operator, diamond A, is often defined as not box, not A, and may be read as A is consistent with what is provable. Provability logic can be interpreted using several kinds of semantics. One common approach uses possible world semantics, in which formulas are evaluated at possible worlds connected by an accessibility relation. In provability logic, these worlds can be understood as stages of reasoning or states representing different levels of proof. The accessibility relation in such models often satisfies special conditions reflecting properties of provability. For example, the relation is typically transitive and conversely well-founded, capturing the idea that proofs cannot descend indefinitely, but consist of finitely many sentences. A relation is conversely well-founded if, and only if, there are no infinite ascending sequences of the form W2 is accessible from W1, W3 is accessible from W2, W4 is accessible from W3, and so on, where W1, W2, W3, W4, etc. are possible worlds. If a relation is conversely well-founded, it is not reflexive. Another important semantic perspective is arithmetical semantics. In this interpretation, formulas of provability logic correspond to statements about provability within formal arithmetic. The modal operator box is interpreted as an explicit provability predicate. Under this interpretation, provability logic captures principles that are valid for provability in arithmetic. As in other modal logics, logical consequence in provability logic can be defined semantically. A formula is valid if and only if it is true at every world in every model that satisfies the semantic constraints of the logic. In arithmetical interpretations, validity can also be understood in terms of provability in formal systems. A principle of provability logic is arithmetically valid if, under every appropriate interpretation, the corresponding statement about provability can be proved within the arithmetic theory being studied. Thus, provability logic connects semantic notions of validity with syntactic notions of proof. Several proof methods are used to study provability logic. These include Hilbert-style systems, which use axioms and rules of inference to derive theorems. The system GL is obtained by adding the following axiom to the smallest so-called normal modal logic, K. If it is provable that A, then it is provable that A. This axiom is often called GL, so GL can refer both to a system and to a sentence. Sequent calculi, which structure proofs as sequences of inference steps involving sequence. Tableau methods, which attempt to construct countermodels to test validity. Fixed point constructions, which are important in connecting modal formulas with self-referential arithmetical statements. Provability logic has been extended in several directions. One important extension introduces polymodal provability logics, which include multiple modal operators representing different notions or strengths of provability. These systems are used in the study of hierarchies of formal theories. Another extension involves combining provability logic with predicate logic, allowing quantification over mathematical objects. Provability logic has also been combined with temporal and epistemic logics to explore connections between proof, knowledge, and time. Such extensions broaden the scope of provability logic and connect it with other areas of logic and philosophy. Provability logics often possess well-studied metalogical properties. Many systems are sound and complete with respect to their intended semantics. For example, the system GL is sound and complete with respect to a class of transitive, conversely well-founded possible worlds frames. Other important metalogical properties include decidability, meaning there is an effective method for determining whether a formula is a theorem of the logic, and the finite model property, which ensures that non-theorems can be refuted in finite models. These properties make provability logic both mathematically tractable and philosophically informative. Extensions of GL may lose these properties. Provability logic provides a framework for studying the concept of proof within logic and mathematics. By combining ideas from modal logic, proof theory, and the foundations of arithmetic, it allows logicians to investigate the structure and limitations of formal provability. Although it began as a tool for understanding Gödel's incompleteness theorems, provability logic has developed into a rich and active field with connections to many areas of logic, mathematics, theoretical computer science, and other subjects.